Good afternoon, Dr. Kim. We're Einstein Group Incorporated, and this is our design review report presentation. And my name is Joshua Williams. I represent the software developer of the group. And I'll let my senior introduce himself.
My name is Tristan Youngblood. I'm the systems engineer.
Henry Funny, digital hardware design.
I'm Orion Patterson. I'm the analog design. We just want to open up with a little introduction. Here's a quote by an engineer. Strive for perfection in everything you do. Take the best that exists, make it better, and when it does not exist, design. That's basically what engineers do. In our introduction, during the duration of this presentation, we, the Einstein Group, will in depth present our senior design proposal through our extensive research and development over the fall 2013 semester. During the presentation, we'll go through about 12 slides of our main slides of our products and everything we've done over this semester, including restatement, objective statement, problem specification table, level 0, 1, 2, and 3, non-trivial unit diagram, test plan document, work breakdown chart, a Gantt chart, cost summary table, and at the end we'll be doing a demonstration demo.
As previously stated in our other presentation, the world is slowly moving towards autonomous vehicles being out freely on the highways and in the neighborhoods. Soon, BMW and other companies like that claim to have out next year. But the basic between the needs are that people need an autonomous vehicle that requires little to no user interaction, and that is cost friendly. Our job, on the environment single, says the toy will serve as a model for a car that can travel across any distance without much user input. What we're going to do is put together a toy vehicle that using MATLAB user-friendly GUI system will be able to travel across any distance and maneuver its way without around any obstacles placed before it.
Here we have the requirement specification table, which we took each engineering requirement. We took 8 of them actually, and we listed them as from the most important to the least important. Now we found that the most important is that the device should be able to be incorporated in environment situation, which obviously that would be the best marketing requirement. Which is obviously highlighted in blue here. And that's what we chose. We chose this because in the world today, even though you design something, you still need to market it, and you need to make some kind of revenue off the product. So that's why, again, we felt like this is the best engineering requirement that we should choose. Justification for that choice is the device will be applicable in civil, government, and private application in all life scenarios.
So I'm going to go to the basic systems of the unit that we're working on. So I'm going to talk about 3 levels. The level 0, which is the most basic component. The level 1, which goes a little bit more in depth. And the level 2, which is going to go more in depth on one of the parts that we're actually going to be testing in general. So the level 0 component is basically just going to, the most basic form, which just shows 2 inputs, which are the motion controller and the power supply, and the output, which is the 6-volt DC motor. And this is just the most basic form, just to get your idea how the system is going to work from the outside looking in. So when you go into the level 1 block diagram, you're going to look at a more in-depth feature of what's going on inside the system in general. And this is just showing that the motion controller is going to be connected to the Wi-Fi transceiver, which is sending a signal to the DC motor controller, which is being powered by our power supply, which is sending up to 5 volts DC voltages into each of these units to power them, which in total will send output signal to our 6-volt DC motors and control them in the way that we want them to be controlled. Now, for our level 2 block diagram, we're going to talk about what's going on inside our motor controller. The PowerPoint kind of made the lines really messed up. But basically what's going on inside the motor controller itself is there's multiple different types of components. From the input, you see power supply entering in to our H-bridge, our charge pump, and our logic supply, which are controlled from our power regulators and our protection logic. Now, for our demonstration, which we will go into later, we'll be looking at the H-bridge. And this component is being inputted from our 5-volt power supply and our gate-driven protection logic, which basically is our voltage / current regulation and basically our digital logic inputs. And basically this basically going to control this H-bridge is going to control what is going to be outputted to our DC motors and how we're going to get our wheels turning and moving forward, backward, return left and right.
This is a UML diagram. Instead of doing just one process of our vehicle or component, I decided to do one of the entire system from the user turning on the power all the way down to finishing the setup. But when the user comes to the program and opens it, like now she will turn on the power, and there will be some type of I'm thinking LED system or some type of confirmation that once the user connects to the actual vehicle, you'll be able to tell, like, maybe a green light or something that shows that you are connected to the vehicle and it can receive and send information. After that, using the GUI controller, which will be shown later in later presentations, you'll be able to, the user will be able to select a track, like make his own test path for the car to actually travel. And once the user has, confirmed that this is a track that the car is going to travel, then the program is basically out of the person's hands and the intelligence feature will kick in. Because then, if an obstacle is placed within the car stack, once the track is selected and the program is executed, the car will either, have the option to slow down or turn around that particular obstacle and continue on the path that it was originally given to get to a certain point.
Here, this is our test document. We use unit test / step-by-step test. Basically, this test is application of the GUI process, which is making sure that the unit is reliable and following the given commands. So, for example, for the given commands we have here, if we through the coding, MATLAB coding, if we did nothing, the car shouldn't do anything. Obviously, if we gave it the command to turn right, the wheels should turn right if the car is just is at a standstill, and then so on and so forth. So this is our test document, and then we'll be doing a more in-depth explanation of the test document in our demonstration video.
Okay, so briefly, I want to go over the breakdown of each of my members' work that we plan on doing next semester. Mainly it's going to be me and Orion working on the hardware portion, which of course is going to start off with everybody ordering our parts and us trying to build the motor controller system. At the same time that we're dealing with the hardware portion, or the integrating the power source, the integrating the sensor technology, and the connecting the Wi-Fi and all that, Henry and Josh will be working on the software portion for next semester, which will be programming the hardware, connecting the system to MATLAB, finalizing the GUI and stuff like that. And then in the end, once we load the system with the program, we'll just be testing and troubleshooting from there on.
This is a Gantt chart. Basically, it's a graphical representation of what we just told you. How we plan and how things are going to go. Now, obviously, there's going to be room for, maybe some things don't come in on time or we need extra time to complete some things. But this is, it will be updated to show that this is how we plan it. Maybe something runs maybe a day or two past what we planned, it will be updated to show, you know, how things go, and in case our project wants to be replicated, a person can estimate how long it should take for completion.
Here we have the cost summary table. This is basically just parts of what we need for our project. It breaks down from the source and the comments here of where and what the part is needed for, where the part came from and what it's needed for. We have the quantity and material name and the total pricing of each part. Now here we have obviously the Wi-Fi DC motor controller, the breadboard that goes in to the toy car, the rechargeable battery pack, and the 6-volt battery charger. If things were to change over the next semester that we need more parts, then this table could vary. But these are the main parts that we have for our project. Seeing that you, Dr. Kim, have already given us the motor for our toy car.
Alright, so we're basically going to transfer into a demonstration portion of the presentation. I'm going to briefly go over with you a little bit of the history of our product. We're doing autonomous vehicles, so there isn't any like real definitive history on the product since it's still relatively in the making currently by companies such as Google and BMW, Mercedes, like that. So we already spoke to you earlier about Google and how they use sensors to like digitally map out the surrounding environment to kind of avoid collisions and avoid obstacles in the environment. But also, like I said before, BMW, Mercedes, Lexus, they've already come out with, I guess, semi-autonomous cars being in the aspect that they assist you in parking and not fully drive the vehicle for you. I know that next year Mercedes plans on coming out with a fully autonomous car that'll be able to drive up to speeds up to 35 miles per hour or something like that. Other than that, there isn't really any clear, definitive examples of history and of the product that we're currently doing. So once we finish our product, we'll pretty much be put in that category, pretty much opening that forefront.
What's about to happen is, Josh is about to break down, you know, the H-bridge portion of the level 2 diagram that you were previously, we got you on. It's gradually assess the functions of the front wheel, the back wheel, and the turning functions. So that's just the basics of it for this particular demonstration.
What is that?
The H-bridge portion.
That's the
So this is the H-bridge portion of our motor controller. Basically, from our data sheet that we have from our motor controller, basically I grabbed that schematic and I went and put it on P-Splice. And because we don't have the part on this right now, so basically I wanted to actually make a simulation of it before we actually decide to order or run it, just to see if it will work in general. And basically for each part, this is supposed to represent the 5-volt inputs that will go into the motor controller itself. Green represents the front wheel, red represents the back wheel. And this right here represents the digital input that comes from the logic protection gate. Because basically how the motor controller works, it either has to be 1 or 0 for the motor controller to actually turn on. If it's 1, 1, it says that I was told that the unit probably will actually blow up, and if it's 0, 0, it won't turn on at all. So it has to be pretty much essentially exclusive OR gate. So 1 or 0.
How are you going to give a 1, 1, 0? What is the input?
It's represented right here.
That's the input?
Yeah, it's basically, we're talking about the digital input or the voltage input.
Yeah, I think in order for this to be one, that would be one, and opposite to be 0, how would you change that?
That's a ground.
Oh yeah, that's the 0 right there, so it's nothing. That's
Right.
0. And this is essentially
So how are you going to give a 1, 0?
How would I get a 1?
Yeah,
0?
where?
Oh, attach a source to here, and that'll be your 1. and Pastor Brown would do to be a zero. I mean, because when I was working with the actual schematic had a semiconductor attached to it, but this didn't have the actual library I needed for the semiconductor to actually use the actual 0 1. So I came up with my own little type of way of doing it, so I can just get a basic version going.
So you said that the green is going to be a back wheel,
It'll be the front wheel,
front wheel.
and red. be the
Red
back
is blue. So when you give a 1 0,
Mhm.
then
They
you know,
both all
front wheel is going to change. That is not moving at all. So where?
No,
I'm asking you where I give you 1 0.
You get 1 0 here. This is where you get it.
Which point? There's a red point.
No, like 1 0 is right
Red-
here. Like, cause
How
basic-
is it?
Mhm.
Is a red point is a 1 0? Where
No,
where
red
is
zero
it?
is right here. 1 0 0. Like it's gonna be you can put 0 1 right here, and you put 0 1 right here. Like you can put them at both these endpoints right here.
You don't understand what I'm asking. 1 0 is coming. That's a logic, right?
Mm-hmm.
Logic 2 point. 1 1 0.
Yeah.
Where are you going to put it?
Where am I supposed to put it?
Like for instance, this one would be 1.
That's a 0. You're ground. You know, this is a ground.
This is just for example purposes. In the actual demonstration, we'll actually have a source right there. Like you said, we'll have a semiconductor right now. Just based off visual purposes, we just want to have something there, and we're trying to explain to you. I think you already tried it. We didn't have a semiconductor, or we couldn't find a semiconductor for this diagram. But in the actual,
You know, you said that that's a 0, 0 and 5. There's a positive side of the 5 point. There's a 0 is ground point. You know the ground point in the circuit?
Yeah.
So there's 2 points is a ground point.
Oh, this is just meant like because like the simulation wouldn't work by then attach ground to these.
Yeah, that's a ground point.
Yeah.
So what I'm saying, where I can give you 1 0.
If you would take the ground off. If you would take the ground off, if you took these ground off, you put 1 0 at these points right here. These were the 1 0 would come in. That's exactly what you.
Okay, go ahead.
Alright, so let me at least show the simulation being ran itself. So let's say since these are both at 5 volts, since these are both at 5 volts, you would assume that the car would be going forward and turning right since it's at positive 5 volts on the front wheel and positive 5 volts on the back wheel. So right here, what's being shown is that they're both at 5 volts since the front wheel is at 5 volts and the back wheel is at 5 volts also since it's moving forward and turning right. But if you were to decide to want to change where say you want to make this backwards or turn left. This is to make it turn left instead of negative. It's at negative 5 volts and 5 volts, so it's turning left and going forward. And you wanted to not do anything, not move at all, like say you just wanted to go straight. You attach it to 0, it would be 0 volts right there on the simulation. You have 0 volts, 5 volts. See, it's basically just following what type of impulse you input into it, and what will be output is how the wheels will be controlled. And that's just a general run of how our demo demonstration is done. And to conclude, To conclude, basically, we believe that the autonomous car is the future society, that the technology is here, the engineers are ready, and the world is calling for a safe, efficient, eco-friendly, financially acceptable self-aware car. And we here at EGI hope that we can fulfill our consumers' need, and that we hope that you're ready to progress with us for the future of technology. Thank you.